And I'm not gonna reveal point that.
Okay, so here's the situation we've got. Let's say we've got a cube full of fluid, and so here's my cube full of fluid. And so the top's open, right? And I'm going to, so here's the water level inside this thing. Right, so it looks like that. There's the water level. I'm gonna put a plunger it's gonna seal very tightly. So the plunger is going to fit exactly into the square opening, and I'm gonna push down on this fluid. Okay, I'm gonna push down on this fluid, and by the way, the dimensions are 2 meters per side.
2 meters.
2 meters, so it's a 2 meter by 2 meter by 2 meter cube. And I'm going to press down with this flat, here it is, you can see there's my flat plunger, right, that I'm pushing down. I'm going to push down on the fluid. I'm going to let the air escape first, and then I'm going to press down on this thing. Okay, and I'm going to press down with a force of 1,000 newtons. Okay, what's the pressure going to be in the fluid?
Q.
Does not matter how much water is in there prior to
It doesn't make any difference. It doesn't make any difference.
Is it,
250.
yeah, 250.
How'd you get that?
Force over areas.
Force per unit area, exactly. Good, so you're gonna know, we know that the cross-sectional area of this thing that's pressing down on the fluid, it has an area of 2 meters by 2 meters, which is 4 square meters, right? And the definition of pressure, which you learned in science long ago, pressure is just force per unit area, right? So we're just gonna get 1,000 newtons divided by 4 square meters, which is 250 pascals, but just 250 standard units of pressure, right? Okay, so what about, I'm pressing down though, right? So let's say we're gonna build a little, in the bottom of this chamber. So here's my chamber. We don't want to have all that pressure. We're in the water and we don't want to feel all that pressure. So we're gonna build a little structure down here to get away from the pressure. So the structure is gonna be a hemispherical. Well, actually, it doesn't need to be that. It's just gonna be like a canopy, like so. It's just sitting on the bottom of this thing with a solid top, and I'm pressing from above. So if I stand under this thing, I ought to be fine, right?
No,
How come?
because the fluid's going around it.
Because the fluid's going around it, good. And pressure is transmitted in all directions equally in a fluid, right? So I'm not just gonna get pressed down, I'm gonna get squeezed from all directions uniformly with that pressure, right? Does that make sense? Okay? That's scenario one. No big deal, right? No big deal. Scenario two. This time, I'm telling you that I have a sealed cube of water, any fluid for that, any non-compressible fluid for that matter, like water or oil, or we just don't want to use a gas. Because a gas you can compress. But we've got this sealed cube, and this time I'm telling you for certain that the pressure inside this sealed cube is 500 pascals. Okay? I would like to know, it turns out that the welds on one of these, one of the seams around one of the faces are kind of weak. And so I want to know, are we in danger or not? I need to know how much force is being applied to that surface, okay? This time, this is a cube that's a little smaller. It's just 0.5 meters per side. I gotta know what the force is acting on that side though, to know if the welds are gonna hold. What am I gonna do?
Square, is it 250? No. 250 times 75.
It's about
Okay, so
2,000
what are,
meters.
Richard, what relationship are you using here?
Force equals pressure, or force divided by area equals pressure.
Okay, good, so you're saying pressure equals force over area, and you're just solving for force, right? I'm not sure if you had the right equation, but I knew what you were thinking though. So force equals pressure times area, right? So the force acting on the top here is gonna be pressure, which is 500 pascals, 500, just standard units, right? The units that we build from kilograms, meters, and seconds, so they all play nicely together, times the area. Well, what's the area? 0.25 square meters, right? And what is a Pascal? It's a Newton per square meter. So we're gonna end up then with the force acting on the top is 0.25 times 500, which is what? 125 newtons, okay? Now I've got a similar cube. I've got a similar cube that's also filled with water, and it's got the same pressure, water's under the same pressure inside. Only this time, it's only 0.1 meters per side length. Okay, what's the force going to be acting on the top of this one? More or less? What do you think?
Less.
Let's find out. Pressure times area, so we're going to get
Something would be
500
5 newtons.
newtons per square meter times 0.01, right? Square meters, so that's not very big. 5 newtons compared to 125, right? It's a lot less. Big discrepancy. It's a big discrepancy because area goes as the square of side length, right? See what I'm saying? So this isn't just 5 times smaller. The area is 5 squared, or 25 times smaller, right? And 125 divided by 5 is 5. Yep.
So is that why there's no oxygen tanks that are like huge? They just have a lot of small oxygen tanks?
Well, yeah, having a big tank would mean that you would have lots of pressure. You're right. Now you have a longer weld, right? But you're right. I mean, it's easier to contain high pressure in something small than something big. Okay. So then, hydraulics. Now we understand hydraulics. Let me explain. This is all a hydraulic machine does. You've got a master cylinder that contains a hydraulic fluid. Okay, it's going to be an oil fluid so it doesn't rust anything, right? And it's connected with rigid tubing to a slave cylinder, which is actually doing the work, which is attached to the machine, right? And it could go either way, depending on what you're trying to do with this hydraulic machine. If you have a hydraulic press, where you're trying to squeeze something with tremendous force, then this is going to be the master cylinder and that's going to be the slave cylinder. Because, look what this does. We can push down with a relatively small force, right? If we push down with a relatively small force here, we're going to get high pressures because what's the relationship between pressure and force and area? Pressure is force divided by area, right? So the area of application is pretty small. So for a given force, because we've got a small area here, we get high pressures. If this is connected with this hydraulic line so oil can flow freely between the two cylinders, what's going to be the impact here? Well, here we've got the same pressure inside, but it's acting on a much, much larger area. So what's gonna happen? Force is gonna go up, isn't it? Right? One way to visualize that would be over here, constant pressure equals small force, small force divided by small area. Over here, we've got same pressure, but it's gonna equal a big force divided by a big area, right? Because they have to be the same ratio, right? So if the area gets bigger, so does the force need to be. If you solve for F equals P times A, right? So the pressure is fixed. You've got a small force equals constant pressure times small area. Up here you've got large force equals constant pressure times large area. They're directly proportional, right? See how that works then? So you end up applying small force here and it's magnified greatly. You get much larger forces here. How much? Ratio of the areas, right? Let's do a quick example. So let's put some numbers on this. So let's say that this cylinder, do I have one with numbers? Well, maybe not. Yes, I don't. Okay, so let's say that rather than using D, let's use R. So if the radius of this guy is going to be little r, okay, and the pressure is just going to be P. So if we're applying force little f there, what's going to be the pressure? So what's the pressure that's acting on the fluid here? Force. What's the area going to be if the radius of this guy is little r? No. Pi r squared. Okay. What about over here? So this is going to be big R, right? And we'll solve for F. We'll call it big F. But we'll solve for it in terms of the other parameters. So the pressure here is going to equal big F divided by pi times big R squared. The pressure is uniform throughout, so we end up with the relationship big F over pi big R squared equals little f over pi little r squared. So we can multiply both by pi and get rid of those. All I got to do is multiply by both sides by r squared, right? So F equals big R squared over little r squared times the input force. Okay, well, let's attach some numbers to this. So what if the master cylinder here has a, let's make it pretty small. Let's make it have a radius of 1 centimeter. Okay, so here if R equals 0.010 meters, let's say. Yeah, and over here, let's make this a really big cylinder. Let's make it have a radius of 1 meter. So it's a really big cylinder. So capital R, 1.0 meters. What's my ratio going to be then? What's the output force going to be? So the output and the input force, we'll just leave it F. What's this ratio going to end up being?
1,000.
It's going to be 1 squared is 1, right?
0.01 squared.
Over 0.01 squared is going to be 0.0001. So I'm going to get, actually,
Is it 1,000 or 10,000?
10,000, yeah. It's going to be 10,000. So the big force is going to be 10,000 times the little force.
You also have to go 10,000 times the distance with the.
Right, right. So that means you're going to have to push it through the fluid 10,000 times further. And that's a pretty extreme, that's a pretty extreme discrepancy in cylinder size. But if you're doing something like a hydraulic press, where the thing only has to move very slightly, but you got to really compress, like compress metal and make it completely flat. I mean, 10,000 times, that's a pretty big deal. I I could press down with a machine. If I press down with,
It doesn't
you know,
work
a
your machine.
1,000 newtons of force, I'm getting back 10,000, I'm getting what? No, not that, I'm
10
getting
million.
back 10 million newtons of force, compression force, right? And is there gonna be a lot of frictional loss here?
No.
Not really, right? Not much at all, really, because fluid is flowing freely through the lines, right, the fluid lines. There's gonna be a little bit, what's, practically speaking, some of you guys probably worked on cars a little bit, what are you gonna do to ensure that none of the fluid leaks out? How do you do that, you know? Like, what do you do if I've got a cylinder I've got the cylinder moving up and down inside this bore, right? The piston's been moving inside the cylinder, so here's the piston. How do I move that thing up and down so no fluid escapes? Do you know?
Gasket.
Yeah, what's a gasket?
It's a little rubbery.
What is it?
It's not like a rubber.
Okay, it could be rubber.
Or some sort of seal.
It's got a seal against the sides though, right? It's gotta be a really tight fit so fluid can't get through, right? So it could be, in some cases, if the pressures aren't super high, you could use rubber, but if they're super high, you can't use rubber. You have to actually use a metal gasket. You have to use a soft metal inside of a hard metal. And the soft metal will literally, I mean, it'll just kind of conform to the cavity then. But you know, it's all greased up, it's in oil, and so the thing slides pretty easily along the sides, right? And that's how you create a seal. And you have to have some kind of a ring in there that's gonna slide along the sides, but it's gonna maintain the fluid. So do you wanna use a fluid then that's more or less viscous, do you suppose? There's a little bit of engineering here, isn't there? Because you want something to be a little bit more viscous so it's not gonna escape through the gasket, through the seal. But you don't want it to be too viscous, how come?
It's harder.
Harder to push through the tubing, right? So what do we use? Oil. We don't use water, we don't use alcohol or something like that that's where the viscosity is too low. It's too hard to trap it then. What if you had a really powerful engine pushing on this thing and you wanted to be able to move something through a big distance? What would you do? Which side are you gonna push on?
The big side.
Big
Yeah,
side.
you can push on the big side, right? Okay, make sense? That's hydraulics. That's all it is. It's really just a simple machine, isn't it? I mean, it's kind of a souped up simple machine, but it's the same exact principle as all the other stuff, all this other stuff we talked about. How would you figure out the actual mechanical advantage? All you're gonna do is just compare the output force to the input force. So in this case,
Is it
mechanic,
with hydraulics, is it gonna be really close?
in terms of the two, well, I mean, there's gonna be
Ideal and.
there's going to be some losses because you do have to, you have to push the piston through the cylinder, right? And there is going to be some drag on the side, but it's not huge. It's not huge. It's better than a pulley, right? So in this case, you'd have 10,000, right? Would be the theoretical mechanical advantage. How do you suppose you could calculate? What do you think the equation would be for calculating the ideal mechanical advantage? Yeah, you bet.
Wait, isn't that it, just right here?
It is. So what's the ratio of what?
Of the areas.
Yeah.
Ratio of the areas.
There you go. Yeah, you bet. Right, so the ratio of the areas would be that's how you could calculate the ideal mechanical advantage of a hydraulic machine that way. Okay, so I am gonna let you guys, I'm gonna put up the other simple machines assignment, and you guys can work on that a little bit. I'm gonna add one little bit on Monday, and then we're done with simple machines.
When will you do that?